In this integral, we're going to talk about how we can compute double integrals by making a change to polar coordinates. So sometimes when you're given a region to integrate over, it's much more easily expressed in polar coordinates than in rectangular. Or in some instances, the integrand is much simpler to express in polar coordinates than it is in rectangular. So let's look at the region xy, ordered pairs xy, such that x squared plus y squared is between 4 and 25, and the x's are greater than 0. Alright, so the equation x squared plus y squared equals 4 gives you a circle of radius 2, centered at the origin, and the equation x squared plus y squared is equal to 25 gives you another circle. This one has radius 5, centered at the origin. Since the values for x squared plus y squared has to be in between 4 and 25, we would shade in between those two circles. And since the x value has to be non-negative, we shade to the right of the y-axis. So this particular region here is what would be described in this particular is what's described by this particular set. Notice that if you were going to try to integrate over this region with respect to x or with respect to y, that would be difficult, right? You've got different bounding curves all the way around. You've got to go from here to here, plus from here to here, and then you've got this region from here to here for x's, and then something similar going on for the y's. So it would make a really, really difficult region to integrate over in terms of x and y. So this is kind of the motivation for why we might want to change it to polar coordinates. Also, notice that this region is very easily expressible in polar coordinates as what's referred to as a polar rectangle. Notice that anywhere that you're in your region, if you come out from the origin out through the region, notice that you always hit this circle and then this circle. You always hit this circle and then this circle, all the way through the whole region. So your r values go from 2 to 5. Those are constants. Also notice that as you sweep, you go from negative pi over 2 down to here, up to pi over 2 over here. So we get that our r value is between two constants, and we know our theta value is between two constants. That's a much simpler region to express. All right, so let's talk about how we calculate double integrals if we're able to change to polar coordinates. So let's suppose by starting with we have a polar rectangle, like we mentioned in the previous one. Recall that the area of a sector of a circle is given to us by half the radius squared times theta. R is the radius of the circle, and theta is the central angle. So for a polar rectangle, we can find its area by subtracting the area of two sectors. Okay, so notice that you would have, if you had from A to B, let's go back to the previous picture here. If you had from A to B, say this is your A and this is your B, this would be one sector for B. I need to subtract off the whole here, if you will. So I have to do a subtraction of the two things. So if our alpha goes from, our theta goes from alpha to beta, the angle would be beta minus alpha. Here the r is b, so it would do 1/2 b squared times beta minus alpha. Do the same thing for the A. Subtract the two. I can factor out a beta minus alpha and a 1/2. I can factor b squared minus a squared. That's the difference of two squares. Notice here that this is the average of the two radii, right? 1/2 a plus b. B minus a is the change in the radius. So I'm going to refer to that as delta r. Beta minus alpha is the change in the theta. So I'll refer to that as delta theta. And you might be able to see that we're going for something with the double integral when we've got a dx and a dy that came from delta x, delta y. Here we're getting a delta r and delta theta. All right, so again, we're using our bar here to represent the average radius, and then the delta r and the delta theta are the difference in the radii and the angles. All right, so now if we've got a polar rectangle, we can do the partitioning much like what we've done with double integrals before. Partition your a to b into m subintervals, alpha to beta into n subintervals, and we get a grid of small polar rectangles. All right, so just like what we did before, choose a sample point in the ith subinterval for r and a sample point in the jth subinterval for thetas. That should be that should be a theta sub j there. The area of each of these rectangles, then, if I'm going to choose the r to be the average radius, the area of each of these rectangles will be r sub I star delta r delta theta. So here's the picture. Here's your r equal to a, r equal to b, theta equal to alpha, theta equal to beta. We calculated the area of that by doing the difference of the areas of two sectors. Here's our partitioning into sub-rectangles here. Here is our r sub I star theta sub j star. And the area of this one rectangle here will be the average radius, the r bar, that r sub I star is how we picked it, times delta r delta theta. All right, so again, first approximate using a double Riemann sum. Notice that we will, these should be j's for your thetas, by the way. This should be theta sub j star in both of those spots. Converting from x to polar is r cosine theta. So that's where that part's coming from. Converting to y to polar, that's r sine theta. That's where that's coming from. So you would take your theta and plug in your conversion formulas for x and y. Notice what goes in for dA. It's the area of the polar rectangle. Technically, I should have an r sub I here, and it's just an r. But this is the area of the polar rectangle, which is r delta theta. So now if we take a double limit, we get an iterated integral that goes a to b for the r's, alpha to beta for the thetas, f of r cosine theta, r sine theta, and then r dr d theta. All right, so the extra factor of r pops in when we convert to polar. All right, so let's look at an example here. Integrand is 1 over x squared plus y squared, and here's our region below. Notice that this region and this integrand is screaming that we should be using polar coordinates because we see that x squared plus y squared piece. All right, as a polar rectangle, our bounds here are 1 to 3 for the r, and pi over 4 to pi over 2 for theta, right? Going from 45 degrees to 90 degrees. And again, like we mentioned, the x squared plus y squared is easily expressible as r squared in the denominator. So now let's just substitute things in here. 1 over x squared plus y squared dA becomes 1 over r squared. That's replacing the x squared plus y squared with r squared. The dA is r dr d theta. The values for r go from 1 to 3. The values for theta go from pi over 2 to pi over 4 to pi over 2. Notice in this case we can split it into two pieces because we have constants for both sets of limits of integration, and there is no theta. So I can do an integral from 1 to 3 from 1 over r dr, and just pi over 4 to pi over 2 for d theta. And if you do the simplifying, this part becomes pi over 4, and this part becomes natural log of 3.